8.3 is on testing a claim about a mean. And we would first separate this between if sigma is known or not known. We're going to first test a claim about a population mean with the population standard deviation sigma not known, which is the more common test that we're going to run. So the requirement of this is that it's a simple random sample and the population is normally distributed or the sample size is greater than 30. Since this utilizes the t-statistic that we've seen before with the confidence interval, so this is a robust process. It could still work with not extreme departure from normality and no outliers. Sample sizes of 15 to 30 will still work for most data sets, but over 30 though for the extreme cases like a skewed right or skewed left distribution. The test statistic is t is equal to the sample mean minus the mean of the sampling distribution of the sample mean divided by the sample standard deviation divided by the square root of the sample size. And this runs to 3 decimal places. This uses a degree of freedom of n minus 1. We can obtain the p-value and critical value from SAS. And some important properties of the student t-distribution. The student t-distribution is different for different sample sizes and degrees of freedom for that matter as well. Probably should note that. The student t-distribution has the same general bell shape as the standard normal distribution. It's what a shape that reflects the greater variability that is expected when the sample standard deviation is used to estimate the population standard deviation. The student t-distribution has a mean of t is equal to 0. The standard deviation of the student t-distribution varies with the sample size and is greater than 1. As the sample size n gets larger, the student t-distribution gets closer and closer and closer to the standard normal distribution. So for example, the authors obtained times of sleep for randomly selected adult subjects included in the National Health and Nutrition Examination Study, and those times hours are listed below down here. Here are the unrounded statistics for this sample. The sample size is 12, sample mean x bar is 6.8333333 hours, and the sample standard deviation s is 1.99240,984 hours. A common recommendation is that adults should sleep between 7 and 9 hours each night. Use the p-value method with a 5% significance level to test the claim that the mean amount of sleep for adults is less than 7 hours. We graphed a histogram here, and we have our normal probability plot. From this, we could see that the distribution is a little hard to determine if it's really normal per se. Looks to be slightly maybe. The normal quantile plot doesn't show any other type of patterns involved, and the points are for the most part, except for like a little bit down here, but for the most part they are close to this line, this green line. So because of this, we could say that the population is approximately normal. So let me write that up here. The population is approximately normal. And we could see the sample size here is 12. So that's why this is important for the population to be. But based upon this, we have the null hypothesis being that the mean is supposed to be equal to that 7 hours. And the alternative, that the mean is less than 7 hours for the sleep time. And the level of significance that we have is 5%. So from this, I'll draw over here the t distribution for this. This has our mean of 7 inside of it. And we want to find the area below 7. And that value here was 6.833333 repeating. And we want the area below it. So here's shaded in red. If we throw this into a calculator or instead of SAS, we could find the t-statistic. This is defined as the sample mean 6.83333 1, 2, 3, 4 3 3 3 3 3 and then one more 3. 6.833333333 minus 7 divided by 1.99240,984 divided by the square root of 12. If you toss this into a calculator, you get an answer of about negative 0.290, and the p-value is 0.3887. All right, and the overall conclusion for this particular test would be, and let me write it down here, at the 5% level of significance, at the 5% level of significance, because this p-value is well above 5%, the 5% level of significance, there is not sufficient evidence to support the claim that the mean, and that's a very bad A, let me very quickly fix that. And I might as well fix my 0 right here too where I'm at. Okay, and the mean amount of adult sleep, is less than 7 hours. Based upon that p-value of 0.3887. The data set to body temperatures data set measures body temperatures with these statistics for 12 a.m. on day 2, N is 106, X bar is 98.20 degrees Fahrenheit, and sample standard deviation is 0.62 degrees Fahrenheit, using a 5% level of significance to test the common belief that the population mean is 98.6 degrees Fahrenheit. This has a sample size of 106. Despite the way the population works, this is going to be approximately normal. The null hypothesis is that the mean is 98.6 degrees Fahrenheit, and the alternative is that the mean is not equal to 98.6 degrees Fahrenheit. We could calculate the t-statistic for this. This would be 98.20 minus 98.6 divided by 0.62 divided by the square root of 106. Tossing that into a calculator, or just using SAS, will give us a t-statistic of negative 6.04. And if we need a t-distribution here just to emphasize it very quickly, we have our mean here of 98.6. A t-distribution of negative 6.04. This is going to be all the way over here-ish, and we have the area below it that we're trying to find. If we toss this into SAS, we get a p-value of 0.000000, which is essentially 0 plus, right? Due to the fact that it's very close to 0, but not entirely impossible. The critical value is equal to positive and negative 1.983. And of course, negative 6.04 is, well, absolutely nowhere near that. We could also find a confidence interval as well if we wanted to. This would be 98.08 degrees Fahrenheit, less than the mean, less than 98.32 degrees Fahrenheit. So the p-value is very low, less than 5%. The critical value shows the t-statistic is well less than that. And the confidence interval shows that the mean is indeed between these two values. The mean that we got anyway of 98.20 is between those two values. The original mean of 98.6 is not above these particular values. So it's closer to this mean, but does not include the mean that we originally tested. And so, because of that, we could then say, in our conclusion, at the 5% level of significance, at the 5% level of significance, there is sufficient evidence to warrant rejection of the common belief so it's the common belief that the population mean body temperature body temperature, not boy temperature. Population mean body temperature is 98.6 degrees Fahrenheit. For alternative methods for deviations and normality, nothing can fix a non-randomized sample, but for the deviation of the population being normally distributed, or the sample being greater than 30, we can use the bootstrap resampling, use the confidence interval method for testing the hypothesis, use a sign test or Wilcoxon sound rings test. The last two will be studied further later in the course. Listed here is a random sample of times and seconds of tobacco use in animated children's movies from the dataset 13 Alcohol and Tobacco in Movies, using a 5% level of significance to test the claim that the sample is from a population with a mean greater than 1 minute, which is the same thing as, well, 60 seconds. And we can see we have our graph down here. This is nowhere near normally distributed, and the sample size is 20. As you could tell, this looks more like almost like a logarithmic type graph. So this is not normal, and the sample size is 20. So that's not good. But we could find the 5th percentile here. That being 29.9 seconds. And the 95th percentile. That is going to be 132.9 seconds. So because of that, we could build our confidence interval here as 29.9 less than mu less than 132.9. As you can see, this is a giant interval due to the fact this is not normal. But we have here that this is not this is a 90% confidence interval. So actually, let me note the confidence interval that we have and not write the conclusion that way. This is a 90% confidence interval. And because we have such a giant range here, and the 60 seconds is within this giant range. So for this, we would have not sufficient evidence to support the alternative where the mean is greater than 60 seconds, since the mean of 60 seconds is indeed in between these two values. Thank you.